Hey mathletes, what's up? It's Mr. Nolde here. Going to look at something called Rolle's theorem today. Did this recently in my calculus class. So we're using the same textbook, and in fact, some of these problems are live from my classroom. So talk to you at the end.
All right, so like I said, we're working on Rolle's theorem today. So Rolle is, actually he's a French guy. I'm probably saying the name wrong. It's probably like Rolle or something. Any event, it has three parts to it. Part number one is that it has to be continuous on a closed interval, has to be differential on the open interval with the same two numbers, a and b, and f of a is equal to f of b. When that happens, there's at least one number, c, in the open interval such that its first derivative is equal to 0. In other words, there'd be a flat line tangent to it. So the easiest way to show it is with this picture here. So if you look at the right-hand side, my other right, left-hand side, from A to B, it is continuous, it is differentiable, and if I set the derivative equal to 0 and solve, I get C, whatever C is. So there is how this theorem works. Here on the right-hand side, notice I have it's continuous. However, with this cusp, it is not differentiable. So even though a maximum exists here, and even though f of a is equal to f of b, it's not differentiable over the open interval a to b on this side. So let's look at a couple of examples. So I'm looking in this section from 9 down to 21. We'll look at the first one, say 9. So this is number 9. And the directions say, identify or determine whether Rolle's theorem can be applied to f. So we need to determine if Rolle's can be applied to this. Has to have a closed interval, continuous on a closed interval, a to b. Has to be differentiable on the open interval, a to b. And if f of a is equal to f of b, then we know that this situation will arise. So the first one's not too bad because it happens to be a polynomial. So we know it's defined everywhere. We know it's continuous everywhere. We know that there's no cusps in it. So the first thing we would do is maybe double check that f of a, 0 in this case, is equal to f of 3. So is this the case? We're going to find out. Let's see. 0 plus 0 is 0. So that's a 0. And for f of 3, let's say I have negative 9 plus 9. So that's also equal to 0. So that is one of the things that is met. Okay, f of a is equal to f of b. Now the other thing, is it continuous? I'm going to abbreviate continuous. Is it continuous on the closed interval, a to b? So on this interval, 0 to 3. And it is because it's a polynomial. And then the last question is it has to be differentiable on the open interval from a to b, which it's going to be. So that means I'm going to take f of x. It's equal to negative x squared plus 3x. And then take the derivative. So the first derivative of this would be negative 2x plus 3. So to find that spot where I'm going to have a horizontal tangent, I set my derivative equal to 0. And that gives me what? Negative 2x is negative 3, or x is 3/2, or 1 1/2 if you like. Some students like to do this. That's fine. Whoops, I wrote 1 1/5. 1 1/2. So we found our c in this case. We found out that, okay, all three of these rules applied, and we set it equal to, took the first derivative, set it equal to 0, took the first derivative here, set it equal to 0, and solved. So we got a critical value, or a critical number of 3/2, or 1 1/2. This time I'll show one where Rolle's theorem does not work. For instance, number 8, or number 13. I said 8 because I saw these 8s over here. But these first, let's see, 4, those are all polynomials, so we know they'll work. But this one, noticed, is not a polynomial because it has this x to the 2/3. So that's going to be a cusp. So does f of a equal f of b. Well, we could try just to make sure, but I do believe it's going to work out. Now remember that 2/3 power means the cube root of x squared. So that would be the cube root of -8 squared minus 1. So that gives me, let's see, -8 times -8 is 64, and the cube root of 64 is 4, and 4 minus 1 is 3. Next, here's my f of b. We have the cube root of +8 squared. So that's going to give us the same thing. That's going to give us a 4 minus 1, which is also 3. So that part of it checks. F of a equals f of b. The x to the 2/3, type it into Desmos or type it into your graphing calculator. The parent function is looking something like this, right? It has a cusp on it, but it is, let's see, -1. So that's going to be moved down 1 unit. So it'll be something like this, right? I'm down here at -1. So is it continuous, right? This is the f of a equals f of b. So check continuous on the closed interval from -8 to +8. Check. However, is it differentiable? I'll abbreviate that. It's not differentiable because of this cusp right here. The derivative does not exist here. So there's not going to be any place on here where I can have f of c, or I'm sorry, f prime of c equal to 0, because what would be, there is no tangent to that. It's just a point. It's a cusp, the vertex. So this is an example where we would say Rolle's does not apply, or however you say that person's name. But Rolle's theorem does not apply. So there you saw one where it did apply and how to apply it, and one where it did not apply. All right, for my final number, we better show like a trig function for good measure. So suppose f of x equals the sine of x. I know that's continuous everywhere, and I know that the sine of 0 is equal to the sine of 2 pi. If I look at a sine function, it looks something like this, where this is 0, this is pi, this would be 2 pi. So the points I'm looking at are going to be this point here and this point here when I take the derivative. So let's take the derivative. So f of x is equal to the sine of x. And the first derivative of that is the cosine of x. So I take this, I set it equal to 0, and that happens, now let me draw a cosine curve. Cosine curve is going to go kind of like this. It's kind of sloppy, but it's 0 at pi halves, and it's also 0 at 3 pi halves. So I'd have, let me switch back to my color. Here are my two answers. These are the two spots on this curve where my slope of a tangent is equal to 0. And we did it over 0 to 2 pi inclusively. So that's a closed interval. So the closed interval had, let's see, f of a was equal to f of b. It was everywhere continuous, and it's everywhere differentiable. So I took the derivative. We got the cosine of x. Scooch that back over. And these are the two solutions. So these are called, remember, these are called the critical values, or critical numbers. Sometimes they're called critical number, critical value, mean the same thing. So that means that Rolle's held up. Check.
All right, so that was it. That was Rolle's theorem. So remember, Rolle's theorem applies, or if it applies, it guarantees the existence of critical points. So that's the end of that. So make sure that in all your classes, you're doing all your homework, you're asking all the questions. Math's not a spectator sport, so you have to participate in math in order to be able to learn math. So until next time, this is Mr. Nolde signing out.